Hey guys, in this video I'm going to do a solution for the whiteboard N2 in Kinematics review. This is a good review for the exam coming up because it combines Newton's second law with some kinematics in a pretty simple case, but one that we can understand. So here's the statement. Consider a crane lifting a car of mass 1350 kilograms with a steel cable. If the car is moving upwards at a constant speed of 0.5 meters per second, what is the tension in the cable? So we were looking for a tension. A tension is a force, so the first thing we should write down is Newton's second law. In order to use Newton's second law, I need to pick a coordinate system, so I'm going to pick upwards to be z and positive. So that means I can write this as the sum of the forces in the z direction is m times the acceleration in the z direction. So how many forces are acting on this object? I can get a free body diagram going on. Gravitational force is pulling the car downwards. The tension is pulling the car upwards, and so the sum of the forces will be T minus Fg. That minus sign is there because I said my coordinate system is straight upwards. That is equal to the mass times the acceleration in the z direction. So I want to find the tension. Fg, that's just going to be the gravitational force, mg on the car. So in order to find the tension, I need to be able to find the acceleration. I'm being given this as a constant speed, so therefore the acceleration is 0, and I can solve this equation, t equals f times g, that's m times g, and if I plug that in, I get about 13,200 Newton. So the tension is exactly the same size as the force of gravity because the car is moving upward at a constant speed. It has no acceleration, so the tension has to exactly balance out the force of gravity. Part B of this problem says if the car started from the ground, how high is it after 15 seconds? So this sounds like a kinematics problem to me because I need to know how high it went if it's moving in a specific way. So the first thing I want to do is write down my knowns and unknowns. So I'm going to call my time t1, that's 15 seconds. I know that. Another known is the position at the ground. I'm going to call that to be 0. And I want to find the final position. I'm going to call that z at t1 because it's the position at that time, and that's an unknown. And now I also need to recognize that I know the acceleration. The acceleration in the z direction is going to be 0. I know this because the car is moving upwards at a constant speed. And of course I can't forget that I actually know the initial velocity. That is 0.5 meters per second. So there's the kinematic equation I want to use. I'm going to rewrite this using the variables I have specified here. That just becomes that because the acceleration az is 0, my initial position z0 is 0, and so I have the final is just v times t, which of course comes out to 7.5 meters. You could have done that in your head, you could have used your intuitive sense to figure it out, but this is how you would use the kinematic equations to make sure that you get the right answer. So now the crane operator wants to place the car into a trash compactor, and so I give the car an acceleration of 0.15 meters per second in the downwards direction. Now what is the tension in the cable? Again, we're looking for tension, we're looking for force, so we should start with Newton's second law. There's Newton's second law, I've specified to the z direction, and then even this is exactly the same thing as we got in part A because nothing is changing about the forces acting on it. Of course, now we have a different acceleration. Instead of 0, the acceleration is negative 0.15 meters per second. Negative because it's in the downwards direction, and I had already specified that t is a positive number, the tension is in the positive direction, and gravity is in the negative direction. So this is a negative number. So now I just need to solve this equation for t. That tells me that the tension is going to be equal to ma times mg, which is m times g plus az. Remember, az is negative, and we get the answer, about 1340. So this is a little bit less than the tension was before because it's accelerating downward. So the tension needs to be less than the gravitational force in order for the resulting car to have a downwards acceleration. Part D says, if the car moves with that acceleration for 13.2 seconds, how high off the ground is the car? Now we're back to thinking about kinematics. We know the acceleration, we know the time, and we want to know how high off the ground is the car. We need to be very careful about our knowns and unknowns in this situation. The thing we're looking for, how high off the ground, is obviously an unknown. Call that ZF, that's Z at a time t2. where here I specified my time t2 to be 13.2 seconds. My initial position should be the position right before the acceleration starts, so it should be the position that we got as an answer for part B, and if you recall, I called that z at t1, so we know that value, that's what we got from part B. Our acceleration is the acceleration from part C, negative 0.15 meters per second squared. The last thing we know is that the initial velocity for the car moving is actually 0.5 meters per second. So that might be a little hard to see, but the idea is that for A and B, the car is moving at a constant velocity upwards at 0.5, and then for C and D, we're making it accelerate downwards, but its initial velocity is what it had in parts A and B. So we need to make sure to remember that. So now we're just going to use our kinematic equations. So there's our kinematic equation in the z direction. We know we have to use this one because we are looking for zf, and the other equation doesn't include zf in it. Now I'm going to rewrite this in terms of the variables in my problem, which is basically just replacing the labeling correctly. But notice that my z0 over here, that's z of t1. This thing was actually equal to v0z times t1, so we put that in there. And then we can just plug in numbers to figure out how high off the ground the car is. And I'll do that. And then go about 1.032 meters. So the car started initially moving upwards with this velocity. I gave it a negative acceleration for 13.2 seconds, and it ended up that it is only 1 meter off the ground in the end. So the final question I have to answer is, the crane stops, so it's accelerating downwards, and then I stop the car, so it's stationary for a second, and then we drop it into the trash compactor, and what speed does the car hit the ground? Get this out of the way. So we're looking for a final speed. We're back to doing kinematics. Let's go and write down the knowns and unknowns. So we know the initial position for this part because it's the final position for the previous part, that was z at t2. Since tension is not acting on this anymore, that's what dropping means. It means that only gravity is acting on it, and so the acceleration is only due to gravity. This thing is in free fall. In addition, the phrase dropping means that the initial velocity is going to be 0 in the z direction. We're looking for the final velocity, so that's certainly an unknown. That's our v of z at t3, where t3 is however long it takes to fall, but then we notice that actually we don't know what t3 is. That is an unknown value for us. So we have two unknowns here, both the time and the final velocity, so we're going to need two equations to solve it. But maybe if we remember that if we don't have time, we have a shortcut, which is we have the third kinematic equation, the one that does not involve time. That's that guy, so let's make sure we have everything we need to use him. This is the final velocity, that's what we're looking for. We hope that's our only unknown. We were dropping it, so that means that this thing is going to be 0. The acceleration, this is free fall, the acceleration is negative g. This delta z, that's zf minus zi. The z final is going to be at the bottom. I should have put that over here in my knowns, that the z at the bottom, at whatever the unknown time is, that's going to be 0. And my initial is going to be this guy right here. So putting in the specific values for this problem, I get that the v squared will be 2 times negative g times negative z at t2, which is the solution from the previous part. And then I can just write that the final velocity is going to be the square root of 2g z at t2. Looking back to get the value of z at t2, I see that this velocity is about 4.5 meters per second. So although it's only dropping about 1 meter, because it's in free fall, it's accelerating at 9.81 downwards. That's quite a large acceleration relative to what it's accelerating before at only 0.15 meters per second squared. So it's going pretty quick once it hits the trash compactor. Okay, great. So that's the solution to this problem. I hope this was helpful, and in particular will help you study for the exam. It's a very simple application of both Newton's laws and the kinematics, but it's something that we need to be able to do before we can move on to doing more complicated things with more than just two forces. Okay, great. Thanks for watching, and I will see you next class.